Welcome to Design an SD Access Fabric. If you're working your way through the ENSLD course, then we just took a look at what an SDA fabric even is. And that's great that we can describe what it is and how it works and the different protocols that we use. But the purpose of the ENSLD exam is to test our ability to create network designs. And so we need to be able to design an SDA fabric. In this video series, we're going to unpack how we design the overlay and the underlay and the border nodes and the control plane nodes, as well as some real-life application. In other words, how do we design an SDA fabric for multiple sites? So come along with me. We'll have a lot of fun exploring now how we design SDA fabrics. And with that, I will see you in the next video. There is no better place to start in an SDA design than the overlay and network segmentation conversation. Remember, the overlay is primarily our network paths. The underlay is great. I mean, that's physically forwarding the traffic, but the overlay is what determines where our traffic goes and how it's forwarded. And in the SDA world, that comes with embedded security. That's great news for us because we don't have to layer security on top anymore. It is baked in to the solution from the ground up. So in this video, we're going to explore, yes, our overlay communications, but a lot of that has to do with network segmentation and how we protect our networks. Let's take a look. When we're looking at an SD access overlay, what we're really talking about are, yes, the VXLAN tunnels that are going to extend from fabric edge node to fabric edge node to fabric border node and such, but also this concept of network segmentation. Because by and large, the tunnel mechanisms, the VXLAN tunnels that we're building, the architecture for this has already been pre-established. What we care about at this point is whether a client, for example, client A here, has the rights to access client B over on the network. Or for that matter, client C that's also directly attached to the same fabric edge node. Network segmentation is broken down into two primary categories. First of all, we have macro segmentation. With macro segmentation, what we're really looking at is segmenting traffic between larger networks. And oftentimes, this is going to relate to multi-tenant environments. In a multi-tenant environment, we think about a service provider who has multiple customers attached to a common network architecture. So if, for example, in our diagram here, we had client D hanging off of this fabric edge node, but client D belonged to a different company than clients A and C, well, that would be a multi-tenant infrastructure. And maybe over here we have another client, client E, and we need to be able to communicate between clients D and E while preventing clients A and D from interacting, because again, they belong to different networks. The way we handle this in SDA is with the concept of a virtual network, or VN. Now, if you're already tuning out or wanting to skip ahead because, hey, Jeff, I don't work for a service provider, it's not a multi-tenant environment that I manage, well, hang on, because we might actually, in some cases, want to deploy virtual networks within a single organization. For example, I might think of a medical clinic where we have one side of the network would be for the doctors and the patients and such. But then on the other side, we might have medical research occurring, and our data governance policy might say that we're not allowed to mix these two networks. Well, in traditional architectures like this, we would have what we call an air-gapped network, where we'd have a bunch of switches and routers on this side all connected, a bunch of routers and switches on this side all connected, and these two shall never connect to one another. But with this macro segmentation concept in SDA, we can now build both of these networks on a single architecture while maintaining distinct network segmentation via these policies. So how does the network identify the difference between hosts from organization A, let's say, and organization B? Well, this comes back to this concept of a virtual network. But specifically, we need to be able to identify to which virtual network a packet belongs. And the way we accomplish this is with the concept of a virtual network identifier, abbreviated as either VNID or sometimes VNI. When a packet arrives on this fabric edge node on ingress into the SDA fabric, we are going to identify to which virtual network this host belongs and then assign a tag to that packet. That tag is going to be the virtual network identifier, which is embedded inside of the VXLAN header. That way, when the packet gets sent across the network to the fabric edge node on the other side, it will de-encapsulate that packet, check the virtual network identifier to make sure that it's going out the right interface, and then send it on appropriately. If, for example, we were trying to send that traffic to client B, which is part of a different organization, well, the fabric edge node at that point would drop the traffic because of the violation in speaking from one virtual network to another. Incidentally, if we do need to speak between virtual networks, we are able to do that with something called a fusion router. The fusion router is going to interact with the border routers, and we're going to be covering that in a little bit more detail later on in this skill. Now, the second type of segmentation that we need to be aware of is microsegmentation. Microsegmentation would be segmenting network traffic within a single network. In a similar fashion to macrosegmentation, we're going to organize our clients into different groups, but this time those groups are going to be called scalable groups, or SGs. We can divide one virtual network into many scalable groups. Each scalable group is going to be a collection of hosts that have similar policies applied to them. And all hosts existing within a scalable group can all communicate openly with one another. So if, for example, hosts A and B are able to communicate with one another, we'd put them into one scalable group. And then maybe host C belongs into a different scalable group. From there, we would define a policy between these two different scalable groups. And the policy might say that we're allowed to communicate with one another, or we're not allowed to communicate with one another, or maybe we're only allowed to communicate on certain network ports. So the next question is, how do we enforce this microsegmentation policy? And it is going to look very similar to what we just discussed with macrosegmentation. When a packet arrives, let's say from host C onto the Fabric Edge node, it is going to get tagged not with a virtual network identifier, but this time with a scalable group tag, or SGT. That SGT is also embedded inside the VXLAN header. So now the VXLAN header is carrying not only a virtual network identifier, but also a scalable group tag. Now the Fabric Edge node can make decisions about forwarding based on that SGT. If, for example, host C goes through the network, lands on this Fabric Edge node, and it's destined for host B, well, we just defined a policy that says host C and B cannot communicate with one another. So this Fabric Edge node is going to drop the packet. Likewise, if host C tries to communicate with host A, even though it's on the same Fabric Edge node, we're going to be able to block that traffic. Because again, we will look at the scalable group tag and make our forwarding decisions accordingly. Now, one key concept you may have already caught that I want to emphasize is the fact that when we enforce that policy and drop traffic, that is occurring on the egress Fabric Edge node. Now, within the world of security, we like to drop traffic as close to the ingress of the network as possible. However, in an SDA fabric, we drop on egress. Why is that? Well, one of the reasons is because if we were to drop on ingress, we would have to have all of these policies for the entire network on every single Fabric Edge node. That's a lot of policy information to store, especially when you scale an SDA fabric out to hundreds or maybe even thousands of nodes. As such, it makes sense to contain that by only deploying policy to a Fabric Edge node for the downstream clients. So yes, that does mean that that packet is going to have to traverse the underlay in order to get to the other side and get dropped. But since it's embedded inside of a tunnel, there's really no security risk in doing that. Furthermore, from a resourcing perspective, our intermediary nodes are primarily just layer 3 devices forwarding traffic, usually at 10 gig links at a minimum. And so we don't really need to worry about resources because these are inexpensive switches with high bandwidth. And so it probably does make sense to reduce the efficiency of our underlay communications while drastically reducing the requirements of our Fabric Edge nodes. So when performing our network designs, we absolutely need to take network segmentation into account. First of all, that might be macro segmentation for a multi-tenant environment, or we have reason to divide into distinct networks within our organization. We'd be looking at virtual networks, and the network uses virtual network identifiers in order to tag that traffic and enforce policy. Second of all, if we do just want to deploy segmentation policy within our network, within a virtual network, we would use scalable groups. And that network traffic is going to be tagged with SGT, scalable group tags, in order to enforce that policy. And lastly, when it does come to policy enforcement, we need to remember in an SDA fabric, that happens on the egress Fabric Edge node. It's not going to be done on ingress like we maybe at first glance might think that that would be our expectation, but the reality is that there are good reasons for deploying it on egress in this case. I hope this has been informative for you, and I'd like to thank you for viewing. In this software-defined world, we love to get excited about the overlay and all of these different policy enhancements that we can bring to the table using SDN. But at the end of the day, we do still have to forward packets on physical equipment, and that would be the underlay. In this video, we're going to take a look at all of the design elements we need to consider when planning out that underlay network. Let's take a look. This is the drawing we use for most of our SDA conversations, and you might have noticed over time that there's this big cloud here. What in the world is going on inside of this cloud? And the reality is that we have a bunch of physical equipment in here. Maybe it's routers, maybe it's switches. And these devices are what the SDA role devices like Fabric Edge nodes and border nodes and control plane nodes, this is how these connect to one another. For example here, if I want to form a VXLAN tunnel between the Fabric Edge node and the border node, well, that's great from a logical perspective. I've got this wonderful logical connection between the Fabric Edge node and the border node, but physically I have to forward that packet into the underlay. At this point, the routers and switches that consist of my overlay are responsible for getting that packet across the network to the Fabric border node, where it can be de-encapsulated and sent on towards its destination. Now, at the end of the day, the role of the underlay is pretty simple in nature. It's simply to forward that traffic from one end of our SDA environment to another. And we can accomplish that in a number of ways, but here's how Cisco recommends that we do it. First of all, they recommend that this underlay be built on layer 3. Second of all, they recommend the IS-IS routing protocol. Because if we think about it, if we're going to forward from this layer 3 interface and this subnet on that link to this layer 3 interface, in other words, the subnet on that link, well, we need to know where those layer 3 networks live, and so that's going to require a routing protocol running in the underlay. And again, Cisco recommends IS-IS for that. Lastly, Cisco recommends an MTU increase, and specifically they recommend setting the MTU to 9100. The reason for 9100 is because a lot of clients can send at 9000, and so that covers the 9000 plus any amount of overhead, including the VXLAN overhead that we've discussed. Now that said, you'll notice that I used the word recommendations. These are not requirements. And so Cisco does allow a couple of other configuration options. First of all, they will allow for a layer 2 underlay. It sounds counterintuitive, but yes, we can deploy our underlay on layer 2. That would be introducing all of the lovely protocols that we've used before, like spanning tree protocol and such, into the mix. Now, this is not ideal. In fact, there are no advantages to deploying layer 2, but at the same time, Cisco will support it because at a minimum, we might need to transition our existing network as we convert it to an underlay. It might be layer 2 today, and we need to slowly convert that to layer 3. Second of all, Cisco will allow EIGRP or OSPF to be deployed into the underlay. ISIS is still recommended from a scaling perspective. However, Cisco understands that a lot of shops are not as comfortable with ISIS because it usually is used more in the service provider space. Lastly, as far as MTU is concerned, we don't need to set it to 9100. We just want to make sure that we're not fragmenting any packets. So if we're using 1500 as our standard MTU, we just need to remember that we need to increase it by the 50 bytes that VXLAN is going to add as an overhead. Now, we have spoke before about how DNA Center, as our SDN controller, can go into the underlay and configure it for us. This is a feature called LAN automation. LAN automation is going to configure this for us. It's going to deploy layer 3. It's going to deploy ISIS as a routing protocol. And it's going to deploy 9100 as the MTU. However, if we're not going to use LAN automation, we're either going to convert an existing infrastructure to the underlay, or we're going to deploy our own underlay how we want. It's fine for us to use their allowances, but keep in mind that when we're calling TAC, TAC is doing a lot of work on underlays that are built on layer 3, ISIS, and 9100 MTUs. And so in a lot of cases, we just want to still build it according to Cisco's recommendations, even if we're not as comfortable with ISIS compared to EIGRP, let's say. Sometimes a good design philosophy is to deploy a solution based on how it's best supported. And again, from a TAC perspective, it might make sense to deploy it as Cisco recommends. Now, we do have a few other requirements, or at least strong recommendations, that we'd want to consider when deploying an underlay. First of all, in most cases, we are going to use a loopback address on the fabric edge nodes and the fabric border nodes in order to form our VXLAN tunnels. And we need to make sure that the loopbacks are getting advertised into the underlay domain. Second of all, speaking of those edge devices, the edge devices need to know where the wireless LAN controllers live. We talked about how the wireless LAN controllers are going to live outside of the border node, but the underlay needs to be able to reach the wireless LAN controller. As such, all of these devices in the underlay not only need to know where the loopbacks are on the edge devices, but also where the wireless LAN controller is. Next, when we're building our underlay connections, we want to make sure those connections are point-to-point. That means that they're directly attached via layer 3 links rather than running through some kind of switched infrastructure. Next, regardless of the routing protocol that we are deploying, we want to make sure that we deploy it with BFD. Bidirectional forwarding detection is going to give us a lightweight way of making sure that we detect the moment one of our routing neighbors goes down. Lastly, from a bandwidth perspective, Cisco has two recommendations for this. First of all, the minimum bandwidth links we should be deploying would be 10 gig. So 10 gig, 25 gig, 40, 100, whatever we want to deploy into the underlay so long as the minimum link is 10 gig. And second of all, Cisco recommends no more than a 20-to-1 oversubscription. In other words, if we have 48 links hanging off of this fabric edge node and we have a single 10 gig link upstream, well, that would be a 4.8 or roughly a 5-to-1 ratio. So 20-to-1 is quite a bit, but at the same time, it's something to be aware of in case we have a lot of different switches hanging off of these fabric edge nodes. And that's about it. When it comes to our underlays, they aren't going to be super complicated. We really just need them to forward layer 3 traffic. And as such, we want to follow Cisco's recommendations as best we can. First of all, the big recommendations they make are that we deploy a layer 3 underlay built on ISIS with a 9100 MTU. If, however, we can't quite meet their recommendations for one reason or another, then they will allow us to diverge from that. First of all, we could deploy a layer 2 underlay. And second of all, we could deploy EIGRP or OSPF as the routing protocols. And third, we just need to make sure that we're avoiding fragmentation. So as long as we increase the MTU by the 50 bytes that VXLAN brings to the table, then we should be good there. Lastly, we want to pay attention to some of Cisco's stronger recommendations. Again, not necessarily requirements in a lot of cases, but for example, we think about the point-to-point links and BFD with our routing protocol and minimum of 10 gig bandwidth. We absolutely want to make sure that when we're building our underlay that it's robust and that follows Cisco's recommendations as closely as possible so that when it comes time to troubleshoot an issue and we need to support this network, that we're able to do so. I hope this has been informative for you, and I'd like to thank you for viewing. As with traditional networks, the control plane is a mission-critical component of our network architecture. However, the difference is that in this case with SDA, the control plane is all riding on one device role in the control plane node. In this video, I want to explore how exactly we should go about designing that control plane node and maybe consider deploying some redundancy to make sure it stays online. Let's dive in. As we've covered up to this point, the control plane for an SDA fabric is going to rely entirely on the control plane node. This is really a Lisp map server on the back end, and it's storing the endpoint identifier to RLock database. In Cisco world, we sometimes call this database the Host Tracking Database, or HTDB. This host tracking database is mission critical because as packets come in, remember, these end devices have no idea where anything lives in the network. We are not using routing protocols to preemptively push any information they may need one day. As such, when that packet arrives and we don't know where it goes, we reach out to the control plane node to find out, hey, which routing locator does that endpoint identifier belong to? This is why this control plane node must be available at all times. If our control plane goes down, then we can no longer forward traffic in the SDA fabric. This is why we're going to recommend that we deploy a redundant control plane node. When we deploy redundant control plane nodes, these are going to exist in an active state. The redundant nodes will have the entirety of the host tracking database on there, and there's absolutely no synchronization between the two nodes. In other words, all of the redundancy configuration happens over here. We make sure that all of our edge nodes know where all of the different control plane nodes are. That's going to happen inside the configuration. At that point, when we perform registrations, we'll perform registrations to both nodes, and map requests will also occur in an active fashion. Now, on an interesting note, we can support up to 6 different nodes in an SDA fabric. However, when we get into the wireless world, we have wireless LAN controllers. Those will only support up to 2 different nodes. And specifically, it can be configured for 2 control plane nodes for guest access, and then 2 control plane nodes for non-guest traffic. However, that still limits us at 2. And so even though our SDA fabric can support 6 nodes, as soon as we introduce wireless into the mix, we're back down to 2 total control plane nodes that we can support at a given time. Now, when we decide to deploy multiple control plane nodes, we keep in mind again that they're in an active state, and that means that we should deploy these 2 nodes similarly, meaning they should share the same hardware configuration. Likewise, sizing should be made based on the amount of endpoints in our environment. We need to make sure that we have the bandwidth and the CPU power and the memory needed to support all of the clients that exist in this SDA fabric. Now, one thing we've mentioned before is that we can collapse the control plane functionality onto the border node. When we do this, this is called co-location. We are co-locating the control plane node functionality onto the border nodes. If, however, we deploy them as separate pieces of hardware, then that would be known as a distributed deployment. So we need to decide between co-location and distributed, and one of the ways we can do that is by looking at the size of our environment. First of all, we recommend distributed for large deployments. We do not want to co-locate our roles when we have a large enterprise scale network. Furthermore, Cisco recommends a distributed approach when wireless roaming is prevalent. However, for small medium sites and for organizations where wireless roaming isn't a major concern, then co-location can be considered. However, the big thing we need to check is to make sure that the hardware that we're going to use for deploying it supports both the border and control plane node roles. Certain hardware types are only border node or only control plane node, and so we need to use Cisco's compatibility matrix to make sure that the hardware itself is capable of doing what we're asking it to do. So, as we can tell from this conversation, the big priority when it comes to control plane design is deploying our control plane nodes redundantly. We absolutely want to make sure that one of those nodes is available at any given time, because if we lose access to that host tracking database, then our entire fabric is going to go down. Second of all, we can support up to 6 different nodes in the environment. However, as soon as we introduce wireless into the mix, that number is going to go down to 2. Lastly, we can co-locate the control plane node functionality onto the border nodes if conditions are right. Specifically, if our environment isn't extremely large and if wireless roaming isn't super prevalent in our environment. I hope this has been informative for you, and I'd like to thank you for viewing. Now that we've designed our control plane nodes, it's time to move on to the border nodes. In this video, we're going to explore not only how the border nodes function, but also the different things that we need to consider when we're performing our designs, including a very important concept, which is whether we need to include fusion routers at the borders. Let's take a look. It's a lot of fun talking about VXLAN and Lisp and how this SDA fabric functions, but at some point we need to communicate between hosts that are attached downstream of the fabric edge nodes and the hosts that are part of our non-SDA domain. In other words, the rest of our network. This would be, for example, the network core and the data center and other WAN sites. None of these network locations will be running software-defined access. And even if we're running software-defined access at some remote sites, it won't be part of the same fabric. This is going to require the deployment of border nodes. Border nodes are going to attach into the SDA fabric, and by all rights, they're going to function very similarly to fabric edge nodes. However, there are some differences, but a lot of that's going to come down to what mode of operation that border node is running in. And there are two primary modes that we need to be aware of. First of all will be the internal border node. An internal border node is responsible for connecting to the rest of the network. That would be internal networks, again, such as the core data center and WAN. But one thing we didn't mention in this list would be connecting out to the internet. The internet is really just the ultimate destination for what we have in our network in the form of default routes. If the border node is responsible for connecting our SDA fabric to the default route, in other words, ultimately to the internet, then this is going to be considered an external border node, otherwise known as an outside border node. Now, even though these are two independent roles, the internal border node and the external border node, we can combine those two different modes of operation onto a single border node. And if that's the case, we're going to combine internal and external border node functionalities onto a border node that we call an anywhere border node. Now, regardless of the mode of operation, the purpose of the border node is to connect our SDA and non-SDA domains. In a lot of cases, what that means is we're going to be running some kind of routing protocol to the rest of the network. This might be EIGRP or OSPF or even BGP. Meanwhile, internally, we're going to be interacting from an SDA perspective. That means Lisp and VXLAN. In other words, we're going to be interacting with the control plane node. So as mentioned earlier, the border nodes are going to behave similarly to the fabric edge nodes from the perspective that we are going to advertise to the control plane node our endpoint identifiers, and that's going to get mapped to the routing locator for that particular border node. The question is, what exactly are we listing as our endpoint identifiers? And the answer to that is going to be the subnets that we're learning from our routing protocols. As I learn of a subnet, for example, let's say I learn 10.1.1.0/24, I'm going to advertise that to the control plane node. And the control plane node is going to know 10.1.1.0/24 is mapped to my internal border node. As such, when a packet arrives on this fabric edge node and it's destined towards that subnet, the fabric edge node will do its thing. It will send a map request to the control plane node, it'll get a reply back, and it will know to send that traffic to the internal border node. The border nodes, just like the fabric edge nodes, are all going to have VXLANs among one another, and so we'll send it out that VXLAN tunnel to the appropriate destination. So it's great that the SDA world knows about the non-SDA world, but the non-SDA world needs to know about the Lisp subnets. As such, the internal border node is going to be responsible for advertising the subnets from the SDA domain up into the rest of the world. Now when packets arrive on the internal border node from the rest of the network, the internal border node at that point will behave just like a fabric edge node. It'll send the map request to the control plane node, figure out which VXLAN tunnel needs to send that packet towards its destination. Now the external node is a little bit different from the perspective that it is not going to advertise anything to the control plane node. The external border node's function is essentially to be the default gateway for our SDA environment. I'm using default in quotes because we're not actually advertising a default network into the SDA world. Instead, the way this works is that the fabric edge node is going to send a map request to the control plane node for a destination that is not known. At that point, the control plane node will send back a negative map reply. It's a map reply that basically says, I don't know where this network lives. At that point, we might expect the fabric edge node to simply drop that packet. However, instead, when we have an external border node configured, the fabric edge node will take that packet, encapsulate it into a VXLAN tunnel, and send it to the external border node. The external border node is our best hope for arriving at an unknown network, and so we're simply going to send all of our traffic to it when we don't know where the destination lives. So from an internal facing perspective, it's a little bit different how it works. Again, we're not advertising anything to the control plane node from the external border node. However, we are running routing protocols upstream in order to advertise the SDA subnets, because we're not necessarily directly connecting to a cable modem, for example. We might be connecting to a network that then lands on the internet or whatever is upstream of this external border node. Now, when it comes to speccing out hardware for the border node, we have the option of using a multi-layer switch or a router. We might want to consider a switch when we need high bandwidth ports like 25 gig, 40 gig, even 100 gig. Or if we simply need a high port count, we'll always get a higher port count on a switch than we will on a router. However, we might consider a router when we have a large number of SGTs in the environment, because routers can usually support more than switches from that perspective. Routers also tend to be more flexible from a QoS perspective and offer functionality like VPNs that we can't achieve on switches. Now, the last thing you need to cover is this concept of fusion routers. Fusion routers are required under two conditions. First of all, we are running virtual networks in the underlying domain. So in some cases, this might be a multi-tenant service provider environment. In other cases, it might just be that we've broken our organization down into different virtual networks, maybe per department. The second condition would be that we need to leak routes between the virtual networks. When this is the case, we will have to install fusion routers upstream of the border nodes. In this case, the fusion routers will perform the routing protocol adjacencies with the non-SDA domain, and we are going to run BGP between the fusion routers and the border nodes. At this point, we will take advantage of BGP operation in order to leak routes among the different virtual networks. However, one important consideration when it comes to our designs is that, at least at the time of this video, the Fusion routers cannot be managed by DNA Center. We are going to have to configure the Fusion routers ourselves manually, which means we are responsible for this BGP configuration. So when designing our border operations, here's what we need to keep in mind. First of all, there are 3 different types of border nodes. We have internal border nodes, external border nodes, and that hybrid role that we call anywhere. Second of all, internal border nodes, they're going to register everything with the control plane node. So they're responsible for receiving subnets from the non-SDA domain, advertising that to the control plane node so the rest of the SDA domain can get to those subnets. Third, we have the external border node, and that doesn't register anything with the control plane node. Instead, when we get that negative map reply back, we send our traffic to the external border node, hoping that it's able to get us to our destination. Lastly, we got to consider those Fusion routers. If we need to do route leaking between our virtual networks, then those Fusion routers will be required and we'll have to do the BGP configuration ourselves. If, however, we're not doing virtual networks or we don't need route leaking between our virtual networks, then Fusion routers aren't required. I hope this has been informative for you, and I'd like to thank you for viewing. So we're doing a software-defined access design. We know what we want in our border nodes or control plane nodes, and we call our Cisco rep and we say, hey, I want a border node, or I want a control plane node, or fabric edge node. And they're going to say, okay, that's great. What type of platform do you want to deploy that on? At some point, we've got to translate all of these roles into actual Cisco platforms. In this video, we're going to take a high-level overview look at the different platforms that Cisco offers within each of these roles, but then most importantly, taking a look at Cisco's online compatibility matrix so we can make those decisions ourselves moving forward. Let's take a look. Cisco has done us a great favor in recent years by consolidating a lot of their platforms under one umbrella, and that umbrella is the Catalyst 9Ks. Notice I didn't say Catalyst 9K switches because the Catalyst 9Ks are more than just switches. But let's go ahead and start with the switches. We have all kinds of different switching platforms, starting with the 9200s, 9300s, 9400s, 9500s, all the way down to 9600s. A lot of Cisco's older platforms have been retired in favor of the 9Ks. For example, the Catalyst 2Ks no longer exist as access layer switches, but instead now the 2Ks have become the 9200s. That second number is going to indicate for us what platform it used to be, so to speak. So the 9300s align with the 3Ks, the 3650s, and the 3850s. The 9400s with the 4Ks, those 4500 chassis. The 9600s would align with the 6Ks, those 6500s and 6800s, or the stalwarts of the networking industry for so long. Now you might be scratching your head and saying, okay, Jeff, what about those 9500s you mentioned? What are those in alignment with? Now, those are primarily in alignment with those 4500X switches. Single rack unit fixed configuration core switches. Now, as mentioned, the Catalyst 9Ks go beyond switches, and we see this in the wireless space. The Catalyst 9800s, for example, are wireless LAN controllers. The 9100s are wireless access points. Now, when it comes to our hardware selection, we need to pay special attention to the different SDA roles that we can support with each platform. For example, the 9200s, those can be fabric edge nodes in our SDA fabric, but they cannot be fabric control plane nodes or fabric border nodes. Meanwhile, the 9300s, these are capable of being fabric edge nodes, fabric border nodes, and fabric control plane nodes. These are really versatile switches. So we have to be really careful when we're selecting our hardware platform to make sure that it supports the role that we want to deploy that particular device into. Let's look at some other platforms. Cisco has the integrated services router platforms. These are routers that are focused on features like voice over IP and even being able to insert UCS servers into the chassis. The ISR 4300s and 4400s are going to be routers that we can add into our SDA framework. Furthermore, we support aggregation services routers, or ASRs. ASRs are going to be focused more on performance than features. For example, you won't find voice over IP features on an ASR, however, you will find large routing table sizes and the ability to support high throughputs of traffic. Now, when it comes to SDA, we are only going to support the ASR 1Ks, not the ASR 9Ks. Next, we have the CSR, the Cloud Services Router. That would be the CSR 1000V. We call it the V because it's a virtual router. It gets installed into a virtual environment. And lastly, we have one of Cisco's latest and greatest platforms in this list, the Catalyst 8000s. Yes, Catalyst is starting to mean way more than a switch. It already means wireless LAN controller and access point, and now it means router. Although Cisco doesn't call the Catalyst 8000s routers, they call them edge platforms. Cisco is essentially evolving the term integrated services router into edge platform to indicate that this is more than just a router. It's capable of doing a lot of different functionality within this family of products. Now, when it comes to routers inside an SDA environment, these devices are only going to be available as fabric border nodes and fabric control plane nodes. However, of note, right now, at the time of this video, the Catalyst 8000s, these are not supported in an SDA fabric. I expect that to change very soon, and so by the time you're watching this video, it's worth investigating to see if that's no longer the case. Because the Catalyst 8000 is the successor to the ISR line, the ASR1Ks, and even the CSR-V. So even though we can still purchase ISRs and ASRs and CSR1000Vs, it's advisable that we take the path of the Catalyst 8000s if we're able to do so. Now, so far our focus has been on if we are procuring new equipment from Cisco. But what if we have existing equipment either on our shelves or live deployed into our network? Can we migrate some of that older equipment into the SDA world? And the answer is yes. We can support legacy hardware as long as it meets certain criteria. For example, we can support 3650 switches and 3850 switches. We can support 4500 chassis and 6500s and 6800s. From a wireless perspective, we can support 3504, 5520, and 8540 wireless LAN controllers. We can also support 802.11 AC, Wave 1 and Wave 2 access points. However, once again, we have to know which roles we can apply to which platforms. For example, the 3650 can only be a Fabric Edge node, whereas a 3850 has more capabilities. It can be a Fabric Border node or a Fabric Control Plane node in addition to the Fabric Edge node. Now, I've called out a few different times that our platforms are restricted in the roles that they can perform. So the question is, how do we know which platforms can be mapped to which roles? And the answer to that is the Cisco SDA Compatibility Matrix. The way we're going to find this compatibility matrix is by going out to our favorite search engine and searching for Cisco SDA Compatibility Matrix. It should be one of the top links here, so let's go ahead and click this link, and it will take us to Cisco's interactive web tool. From here, we're going to select, let's say, New Deployment, and you can choose the version of software here. Usually you're just going to take the latest version of software, especially if it's a new deployment. And from a device role perspective, this is where we can decide, okay, we're going to deploy, let's say, a Fabric Edge node. What are our options for Fabric Edge nodes? We click Submit, and we can scroll down to take a look at our options. For example, we do see some of the older hardware series. We see 3850s and 3650s. We see 4500E chassis switches. And the chassis switches, by the way, are going to require a certain supervisor engine, so we have to pay attention to that sometimes. Furthermore, we can scroll down and see 9200s, 9300s, everything we talked about before, but we do see that the 9600s, for example, don't show up in this list. That means that they are not compatible as Fabric Edge nodes. So let's scroll back up here and take a look at a different search option. Let's go ahead and get rid of Fabric Edge node in our device role search, and we will select Fabric Border and Control Plane nodes. Now we can scroll down and see all the different platforms that are supported here. And primarily we're going to find routing platforms, although we do see some switches on here as well. For example, we start with the ASR 1000s, as we mentioned, the 3850s. We talked about how those can serve as Fabric Border and Control Plane nodes. The 6500s and 6800s, by the way, these are showing up here. They didn't show up as Fabric Edge nodes. We can't actually use those platforms at the edge. So as we scroll down just a little bit further, we do see 6880s, for example, and here we see 9300s. The 9300s are supported as Border and Control Plane nodes. As we scroll down, we're going to find more 9K options as well, 9400s, 9500s, and yes, the 9600s that didn't show up as Fabric Edge nodes. So we're not going to go through every single option here. This is more teaching somebody how to fish rather than giving them fish. I want you to be able to go out to the compatibility matrix and run the appropriate searches in order to make sure that the hardware we want to deploy is supported in the role that we need it to take on. So our takeaways this time are pretty straightforward. First of all, Cisco has the latest and greatest platforms out there in the Catalyst 9Ks and the Catalyst 8Ks as well. Keeping in mind the Catalyst 8Ks aren't yet approved for SDA at the time of this video, but they might be really soon, and so I would keep an eye on that moving forward. However, we do still have the ASRs and the ISR lines in case we need to move forward before the Catalyst 8000s are approved. Now, second of all, we can support older hardware, and so if we've got some equipment out there we want to repurpose, like 3850s, 3650s, 4500s, etc., we've got the ability to deploy that. And lastly, if we want to deploy new hardware or we want to reuse existing hardware, either way, we absolutely need to go out to the compatibility matrix and make sure that the hardware we want to deploy can serve in the role that we need it to. I hope this has been informative for you, and I'd like to thank you for viewing. When studying software-defined access, it's pretty easy to get wrapped up in the wired communications. But the reality is that most of our networks today are built with wireless at the foundation. In this video, we're going to explore all of the different design elements we need to consider when it comes to wireless and SDA solutions. Let's dive in. First of all, we should be clear about one thing, and that is that we don't actually have to integrate wireless into SDA. For example, we could deploy our access points, connect them into the Fabric Edge nodes, and just allow those access points to be treated as if they were end clients. At that point, we would form CAPWAP tunnels up to the wireless LAN controller, wherever that is, and our wireless users who are attaching in through the access points would simply get directed out the CAPWAP tunnel. This doesn't change the fact that we're still running VXLAN tunnels between our edge nodes and our border nodes, for example. And so yeah, we'd be encapsulating CAPWAP inside of VXLAN here. But that's no problem. As long as our MTU is fine and we're not fragmenting, life will be good. Here are the downsides to this. If we're not integrating into SDA, then we're not going to have the same policies between our wired and wireless clients. Remember, we are leveraging Cisco TrustSec for security policy inside the SDA framework. And because these clients would show up as if they were attached logically to the wireless LAN controller, thanks to our tunneling mechanism, these policies would not apply to our wireless clients. Second of all, we'd have to worry about our pathing. If we were to communicate between SDA and non-SDA worlds, we'd have to send all the way up to the wireless LAN controller, get looped around, and come all the way back into the SDA fabric. Even though there's not a lot of what we call east-west traffic in our campus environments, we would still have to account for this in any application that takes advantage of communications directly between clients at the edge. So absolutely, we would want to integrate our wireless network into the software-defined access fabric. The only time we might not want to consider that is if we're in some kind of transition period. Maybe we just migrated to SD access and our wireless is still running traditionally. That's fine. We can support this until we get to the point where we're ready to transition over to integration with software-defined access. So what does it look like to integrate our wireless with software-defined access? Well, the first step is making sure that we're compatible with that. We want to make sure that our roles are such that we can deploy a fabric wireless LAN controller as well as a fabric wireless access point. In the last video, we looked at the SDA compatibility matrix. And so we need to make sure that we have a wireless LAN controller that supports being part of an SDA environment, as well as access points that can participate in the SDA framework. Once we've validated that, we're going to want to connect our wireless LAN controller outside of the SDA fabric. That means that we can connect it to the fabric border node, or we can connect it to some kind of network that exists upstream of the fabric border node. Either way is fine. Now this wireless LAN controller must have access to the control plane node. The reason for that is because the wireless LAN controller will be reporting to the control plane node EID to RLOC mappings. Now when it comes to control plane redundancy, we mentioned this in the control plane design video, we can support up to 6 control plane nodes in the SDA fabric. However, a wireless LAN controller is only able to support 2, specifically 2 for guest applications and another 2 for non-guest applications. However, in most cases, that's still going to mean that we ultimately can't deploy 6 control plane nodes, we can only support 2 in the SDA fabric. Next, we need to think about the access points. First and foremost, the access points are going to have to be directly connected to the fabric edge node. It doesn't work for us to have a downstream switch that's not part of the fabric and then hang our access point off of that. This is not a supported configuration. As such, we're going to need to make sure those access points are directly attached to the fabric edges. Now, if you're working your way through the ENSLD course, then you'll recall that we talked about how wireless works in an SDA fabric, from the perspective that we're going to build a VXLAN tunnel to the upstream fabric edge, but we are also still going to build a CAPWAP tunnel up to the wireless LAN controller. The CAPWAP tunnel is going to be for control information only, whereas the VXLAN tunnel is where our wireless user traffic goes, so that's our data plane communications. In order for us to establish this, a few things need to happen. First of all, when this access point comes online to the fabric edge node, it's going to be recognized as an access point thanks to Cisco Discovery Protocol, or CDP. The fabric edge node is then going to place it into the appropriate VLAN, and specifically, it's going to get tied into the infrastructure virtual network, or infra_VN. This virtual network is special and predefined inside the SDA fabric. And what it essentially means is that it's extending the underlay outside of a fabric edge node. In the past, we've talked about how virtual networks are akin to virtual routing and forwarding instances, and so our inclination might be to believe that this is a separate VRF. However, the infrastructure VN is actually part of the global routing table. In other words, it's the same routing table that exists outside of the SDA world. This is important because it means we're not actually running a separate VRF for the access points. Now this is where things get a little bit interesting, because even though these fabric edge nodes view the access point as something special, they're still going to report to the control plane node that there's an endpoint ID attached to myself. In other words, it's an EID to RLOC mapping. Because they're treated as clients, they can share a single subnet throughout the entire domain. So the access point on the left could be 10.0.0.1/24, and the access point on the right could be 10.0.0.2/24. This means we really only need one single access point IP address pool for our entire network. Once this registration has taken place, the access point is going to be able to form the CAPWAP tunnel out to the wireless LAN controller. In order for this to be a robust connection, we need to make sure we have less than 20 milliseconds of latency between the wireless LAN controllers and the access points. Usually what this means is this wireless LAN controller needs to exist at the same site as the access points that are connecting to it. Once we've formed our CAPWAP tunnels, we're going to receive all the control information that's needed in order to form, number one, the VXLAN tunnels here, but number two, to bring up the wireless communications, which is the point of all of this, so we can communicate to our wireless clients. As the wireless traffic arrives on the access point, it's going to send that, again, across the VXLAN tunnel, and at that point, it becomes part of the SDA framework. The client doesn't need to go to the wireless LAN controller and back. It can simply get routed onto the SDA fabric via the VXLAN tunnels and then arrive at the appropriate destination wherever it's trying to get in the network. So we use the VXLAN tunnel for our client data, and once again, the wireless LAN controller is going to continue to use the CAPWAP tunnel in order to push configuration and radio resource management, or RRM, configuration changes on an as-needed basis. So what exactly do we need to keep in mind when we're performing the designs of these wireless networks? First of all, we keep in mind that wireless doesn't have to be directly integrated with SDA at all. We could run it over the top, we call it, by encapsulating it inside of CAPWAP that's inside the VXLAN tunnels and just kind of bypassing the SDA fabric. We're giving up all of the advantages of SDA, and so eventually we'd probably want to move to that, but it is an option, especially if we're transitioning to SD access, is to do the wireless after the fact. Second of all, when we look at the wireless LAN controllers, they need to be installed outside the fabric, and we need to make sure that they have access to the control plane nodes. Third, we're going to directly attach our access points to the fabric edge nodes, and from there we need to make sure that we have a maximum of 20 milliseconds of latency to the wireless LAN controller. And lastly, once everything has reached steady state operation, we're going to continue to receive wireless control information through the CAPWAP tunnel, but as far as our wireless traffic is concerned, we're going to hand that directly off to the fabric via the VXLAN tunnels. I hope this has been informative for you, and I'd like to thank you for viewing. It's time for everyone's favorite topic, multicast. Whether you like it or not, multicast is going to be part of every SD access design. We are likely going to be integrating into existing multicast deployments, or otherwise just need to adapt for what multicast is going to look like after we've migrated to SDA. In this video, we're going to take a look at not only all of the different ways we can deploy multicast, but also several different options that we have available to us for how we configure it within the fabric. Let's take a look. In most cases, since our SDA fabrics are deployed out into the campus, we're going to find that our multicast sources are upstream of the fabric border nodes. These multicast sources are usually in the data center, but they could be somewhere else in the infrastructure. And in that case, our multicast clients are going to be downstream, attached off of the fabric edge nodes in the SDA fabric. However, let it be known that Cisco does support multicast sources inside the SDA fabric as well. So if that's a need for our organization, then we are covered. Furthermore, from a PIM perspective, SDA is going to support PIM sparse mode and PIM source-specific multicast, or SSM. We are not supporting dense mode in this environment, so keep that in mind in our designs as well. Now, PIM sparse mode requires the use of rendezvous points. A rendezvous point is the glue that connects our multicast source with the multicast receivers out on the network somewhere. In the early days of SDA, our border node was required to be the rendezvous point in a PIM SM environment. However, that caused a lot of problems because in most cases when we migrate to SDA, we already have a rendezvous point somewhere in the network. And as such, we now support both internal and external rendezvous points in the SDA fabric. So whether it's the rendezvous point, the sources, or the receivers, they can be anywhere in the network, inside or outside the SDA fabric. Now when we log into DNA Center to configure multicast, we are going to be presented with two different options for how to configure it. The first option is going to be called head-end replication. When a packet arrives from a source, whether that's on a border node or an edge node, if we have head-end replication configured, then that node itself is going to be responsible for replicating the traffic. In other words, we're going to rely on those unicast VXLAN tunnels, and so in this scenario where we have two receivers on two different edge nodes, that border node is responsible, number one, for determining who wants to receive it. And the way it's going to know that is by paying attention to PIM join messages. Second of all, it has to replicate the packet. It has to create two different versions of that packet, and the last step is simply to forward it out the unicast tunnels. Now, as you might imagine, taking one multicast packet and replicating it into individual unicast streams, in our case, two separate streams, now that's not a particularly efficient way of forwarding multicast traffic. In fact, it outright eliminates the point of how multicast is supposed to function. However, it does come with one advantage, which is that the underlay, the devices that are in here forwarding the traffic, they do not need to be multicast aware. We're not doing anything special in the underlay to make this happen. We're simply taking advantage of the existing VXLAN tunnels that we already use to get traffic to the edge nodes. So the good and bad of replication is that we don't need to configure the underlay in order to support multicast, but the downside will be the efficiency, replicating packets at the head end and forwarding them out individual unicast tunnels. Now originally when SDA was deployed, this was our only option for configuring multicast. Fortunately, Cisco came up with a second option that is called native multicast. This option requires us enabling multicast inside of the underlay. And specifically, it's going to have to be configured for source-specific multicast. At this point, we are going to configure PIM and IGMP and such on all of the routers inside of our underlay. The way this works is when a packet wants to join a multicast stream, let's say it wants to join 239.1.1.1, that Fabric Edge node is going to use this address to derive a new multicast address. That multicast address will be the underlay multicast address. At this point, this Fabric Edge node is going to use the underlay multicast address to join towards the rendezvous point, or in the case of source-specific multicast, the source itself. So in our case, the rendezvous point and the source are both upstream of the Fabric border node, so regardless of our destination, we know that we need to connect to the border node in order to make that happen. As such, we're going to form a multicast tree by sending PIM join messages towards the border node. However, this multicast tree will stay completely within the realm of SDA. We're not forwarding it upstream because there's no reason for that. We are simply using this tree as a mechanism for delivering multicast traffic through the underlay. So let's say we have 30 different nodes on this network, but only the 2 nodes that we have previously drawn here have joined this source-specific multicast tree. Well, at this point, the multicast packet for 239.1.1.1 has now arrived on the border node. The border node is going to simply encapsulate that into a VXLAN packet whose destination is this underlay multicast address. As such, we don't need to replicate this packet at all. We simply send this VXLAN encapsulated multicast packet into the underlay, and because the underlay is configured for multicast, it will perform the replication. It's going to send this traffic in 2 different directions. Keeping in mind, we just said that we have, let's say, 30 edge nodes. We're only going to send the packet towards the destinations as required. So the advantage of native multicast is that it's much better from an efficiency perspective. We rely on multicast to forward multicast traffic. It makes sense. However, call it a downside if you will, but we are going to have to enable multicast inside of the underlay. So that might take extra configuration on our part in order to make this happen. So here's how we can summarize this conversation. First of all, SD Access fully supports multicast. It can support sources inside and outside the fabric. It can support rendezvous points inside and outside the fabric. Second of all, we support PIM sparse mode and source-specific multicast, so SM and SSM inside of SDA. We do not support dense mode or PIM-DM. The third, when we're configuring multicast inside of DNA Center, we're given 2 choices. First of all would be head-end replication. Head-end replication replicates all of the packets itself at the head end, and so it's less efficient, but it does save us some configuration on the underlay. Meanwhile, we can flip that and deploy native multicast. Native multicast does require us to configure the underlay for multicast, but at the same time, it improves the efficiency, and we use multicast to forward multicast packets, which in our designs is probably where we're going to want to land, but again, we just have to make those decisions based on our environment. I hope this has been informative for you, and I'd like to thank you for viewing. Over the course of these 2 skills, we have seen a lot of advantages to software-defined access, and that's great from the perspective of, hey, maybe we should migrate our headquarters network over to SDA. That's great. But what about that small branch office, a remote site that it just isn't large enough to warrant deploying an entire SDA fabric? How can we extend our SDA policies out to that site? In this video, we're going to explore a solution that Cisco gives us as an option, and that would be Fabric in a Box. Let's dive in. Let's say we have just migrated our primary campus over to SDA. And so our SDA fabric is over here looking great, but then we've got this branch site out here, and we have users at this site. And we know that all of our users logging into SDA on this side of the network, taking advantage of all of Cisco TrustSet configuration that we've deployed. But now let's consider the users at that branch site. We would still want those users to be subject to the same policies as our users at our primary location. However, we can't just deploy a Fabric Edge node and tie it into the fabric. We've got latency issues, and just flat out, Cisco doesn't design SDA to spread across our LAN and WAN infrastructures. As such, what we really need is a fabric all on its own. But if we have a site where we have 5 users, does it really make sense to deploy an entire SDA fabric? That would take a control plane node and a border node and a Fabric Edge node at a minimum in order to make this work. This is where Cisco's Fabric in a Box solution comes into play. As the name implies, we're going to deploy a single device, a single box, if you will, to this branch location. This device is going to serve not only as the Fabric Edge node so our users can attach, but also as a control plane node and also as a border node. And this makes it so we can deploy an entire SDA fabric to this remote site by leveraging a single piece of hardware. Now this sounds so great on the surface that many of us might be thinking, oh boy, Jeff, I don't have a huge network. Maybe I should just deploy Fabric in a Box at my primary location as well. But I need to stop you there because Fabric in a Box was not designed to be the entirety of our SDA framework. And a lot of this is going to boil down to some limitations that we have in this solution. First of all, at a max, we can support 200 users on this solution. Second of all, we need 5 or fewer virtual networks to be pushed to that location. Third, we can only support up to 40 access points. And lastly, we can only support 8 IP address pools. Now, these are general guidelines given to us by Cisco, but these limits could actually get more restrictive depending on the hardware that we deploy to the location. So we always need to check the data sheet for the hardware we're deploying in order to make sure that these limitations still apply as we think they do. So now, from a design perspective, we need to ask the question, what is this piece of hardware that we're deploying? And Cisco makes 2 primary recommendations. The first option is probably the best option for us, which would be the Catalyst 9300 switch. On top of being a stackable switch, which gives us some redundancy, we are also able to embed a wireless LAN controller in the 9300s. And specifically, this is leveraging the embedded 9800 wireless LAN controller. If we deployed the 9300 with an embedded WLC, well, now we've got all 4 of our fabric rolls tied up into one box. If we go with a different hardware solution, we can still deploy a wireless LAN controller to this site. It's just going to have to be connected physically into the box that we deploy. Now, the other option that Cisco recommends is the 9500. The 9500 isn't stackable, but it can take advantage of Virtual Switching System, or VSS, for redundancy. However, at the time of this video, we cannot embed a wireless LAN controller into the 9500s, and so deploying a separate box cabled into the 9500s is going to be our solution in that scenario. Now, regardless of the hardware we choose and the configuration that we deploy, one of the advantages to this solution is the fact that we don't need to deploy a new DNA center. Even though DNA center is probably back at this location and it's managing this fabric, it can manage this fabric as well for us. So as we see here, Fabric in a Box is an extremely flexible solution that allows us to push our Cisco TrustSec policies out to remote sites. And the way it does that is by, first and foremost, we deploy a single platform that serves as the Fabric Edge, the Fabric Border, and the Fabric Control Plane node. Second of all, it's intended primarily for small sites. We don't want to deploy our entire fabric on Fabric in a Box. And just keep that in mind when we're doing our designs. This is for multiple site applications. Lastly, we can embed wireless LAN controllers into this solution as well. The way we have to do that, though, is by deploying a Catalyst 9300 with the embedded 9800 wireless LAN controller on it. At that point, we've got a true Fabric in a Box. All 4 of our device roles are on there, but if we don't deploy it in that fashion, we can still deploy a physical wireless LAN controller alongside the Fabric in a Box. I hope this has been informative for you. I'd like to thank you for viewing. In the last video, we started a conversation about this idea of extending our SDA policies out to remote sites. In this video, we're going to cover how exactly we would design that, not only looking at the difference between fabric sites and fabric domains, but also the transit network that has to sit in between these multiple sites. Let's take a look. So far, our conversations have largely revolved around this concept of a fabric that consists of a border node, a control plane node, a bunch of fabric edge nodes. And in the SDA world, we call this a fabric site. A fabric site is a unique set of edge nodes and control plane nodes and border nodes. And optionally, we could include a wireless LAN controller in a fabric site. This is independent of physical locations. For example, when we look at these fabric edge nodes down here, one of these could belong to a closet in building 1, but another of them could belong to a closet in building 2. Conversely, we might, for some reason or another, decide to deploy one fabric site to the entire network, so maybe this is our HQ network, but then we decide to deploy a second fabric site, which would consist of its own fabric edge nodes and border nodes and control plane nodes. And we're going to deploy that to the financial department for maybe security reasons or data governance policies. And even though the finance department lives inside the HQ, we still deliver its own fabric. Maybe it's a Fabric in a Box, or maybe it's just a small fabric site. But the point is that even though we call it a fabric site, it's not necessarily bound to a physical site. Instead, we identify a fabric site by that unique set of edge nodes, control plane nodes, and border nodes. Now, as we deploy multiple fabric sites, we can still manage each individual one with a single instance of DNA Center. In fact, DNA Center is going to represent our fabric domain. A fabric domain is a set of sites that is managed by a single instance of DNA Center. So we need to keep these definitions in mind as we move forward in the conversation. Now, the next topic we need to discuss in this conversation would be how we connect multiple fabric sites to one another. For example, let's say in this scenario we have 3 different fabric sites. We are going to need to establish a transit network that will connect all 3 together. And the goal of any transit network we build should be to extend our policies among the different sites. And we may recall that we have 2 different types of policies. We have microsegmentation policies, which are determined by that scalable group tag. We also have macro segmentation policies, and those are designated by virtual network identifiers. Each of these is carried inside of the VXLAN header, and that's going to carry implications for how we build this transit network. For example, what happens if we receive a packet on the fabric site on the left, and that is destined towards a client that's attached to the fabric site on the top. I would want whatever SGTs and VNIDs are assigned to this fabric site to be able to be identified by the top fabric site as well, so that when traffic is headed towards that client, maybe we can drop the traffic, depending on the policies that we've established. So with that goal in mind, we have two different ways of accomplishing that. The first of which would be if we build an SDA transit network. An SDA transit network allows us to simply build VXLAN tunnels between two different sites. If we can build VXLAN tunnels between our sites, then we can natively carry the SGTs as well as the VNIDs as part of that communications. However, if we're going to build an SDA transit network, then we need some level of control over that network infrastructure. For example, we need to make sure that the MTU is able to carry the VXLAN headers, and we want to make sure that the quality of service markings are respected. In most cases, we're only going to be able to build SDA transit networks on top of dark fiber or possibly Metro Ethernet. And one of the reasons for this is because on top of needing to control the MTU and the QoS and such, we need to be able to attach something we call a transit control plane node to this network. Now, this isn't impossible to build on traditional wide area networking architectures like MPLS and such, but we do see the challenges that are developing. Ultimately, Cisco recommends 100 milliseconds of round-trip latency, but they will support up to 200 milliseconds. So that gives us a nice hard number to look at if, for example, we do want to try to build it on an MPLS network. However, in most cases where we are running traditional WAN architectures, we're just not going to be able to deploy an SDA transit network. In those cases, we're going to need to build an IP transit network. An IP transit network means that we are no longer going to be able to build a VXLAN tunnel between our sites. Instead, we're going to have to simply send de-encapsulated packets across the transit network. De-encapsulated packets means that we don't have scalable group tags anymore, and we don't have virtual network identifiers anymore. As such, once traffic arrives on the remote border node, that border node is going to be responsible for re-identifying the traffic as it enters. This will take more processing by the border nodes, but it means that we can still recover the scalable group tags and the virtual network identifiers. At that point, the traffic gets sent across to the Fabric Edge node, and the Fabric Edge node is going to be able to drop the traffic before sending it onto the client if our policies indicate that that's what's required. So for a lot of architectures like, again, MPLS, or maybe even building it off of a cellular network like LTE, some of these architectures are not going to support an SDA transit network. But fortunately, as we can see, whether it's an SDA transit network or an IP-based transit network, in either case, we are able to extend our policies between multiple fabric sites in the domain. So when we think about multiple sites, we first of all need to make sure that we understand the terminology involved. A fabric site is a unique set of fabric edge nodes, fabric border nodes, and fabric control plane nodes, with the wireless LAN controller being optional. Again, it's not tied down to a specific physical location. Second of all, fabric domain is a set of fabric sites managed by a single instance of DNA center. Now, when we are thinking about all of our different fabric sites and connecting those, we're going to need a transit network, and we have two different transit networks to consider. First of all would be an SDA transit network. The SDA transit network is going to natively carry our VXLAN tunnels across the transit, and that's going to enable us to maintain our scalable group tags and our VNID, so our policy is secure across that. However, if our network doesn't support SDA, then we can deploy an IP-based transit network. An IP-based transit network, we're going to lose the SGTs and the VNIDs, but we can re-identify them on the other side. It's just going to take a little bit more processing in order to do that. But either way, our policies are extended across the fabric domain. Again, managed by one DNA center, that would be our hope. I hope this has been informative for you, and I'd like to thank you for viewing. We've reached the end of this skill, so let's review what we've learned by taking a quiz. First up, out of 5 questions. What tagging mechanisms are used to map microsegmentation and macrosegmentation policy in SD Access? We have 2 different tagging mechanisms we're going to use. For the purposes of microsegmentation, we are going to use those scalable group tags, or SGTs. Scalable group tags tell us which scalable group our packet belongs to. It's going to allow us to enforce policy within a larger network. Meanwhile, macro segmentation is going to help us between larger networks. In other words, between virtual networks by leveraging the virtual network identifier, or VNID. Every now and again, the VNID is referred to a VNI, so you might see that written down in some places. But ultimately, these are the 2 tags that we need to be aware of when it comes to our microsegmentation and macrosegmentation policies. Next up, when are fusion routers required as part of an SD Access design? When we have a fabric, we're going to have border nodes that connect the fabric to the rest of the network. And depending on our design, we might need a fusion router sitting upstream of the border nodes. And this situation is going to arise when we have multiple virtual networks on the fabric, and specifically when we need to leak routes among the virtual networks. Most oftentimes what this means is we have some kind of shared services like DHCP running in our data center, and we want to extend that down to multiple virtual networks. Well, in order to do that, we need to leak these routes back into those virtual network domains, and so the Fusion router is going to accomplish that. If we don't need to do VRF leaking, then we do not need the Fusion router. So A is out. It's not just when we have multiple virtual networks, but specifically D, when we need to do route leaking between those virtual networks or VRFs, that is when we require a Fusion router. Question 3. Which hardware platforms are supported in Cisco SD Access? Now, I want to absolutely stress that when we're talking about which ones are supported, it's as of the time of this video. For example, Catalyst 8Ks are not supported at the time of this video, but I do expect them to be supported at some point in time. We always want to check the compatibility matrix that Cisco has on their website. This is a living document that Cisco updates regularly. Now, as far as the rest of these are concerned, the Catalyst 9Ks are supported, the CSR, that Cloud Services Virtual Router, is supported, and then it comes down to the ASR 1Ks versus the 9Ks. Well, as far as SDA is concerned, it's the ASR 1Ks that we can use. We cannot use the ASR 9Ks, and for the record, I do not expect ASR 9Ks to be added into the SD Access framework. So our answers here are B, C, and D. However, again, always check that matrix when you're doing a network design to find out which hardware devices not only are supported, but also which roles they can be used in. Next question. In which multicast configuration methodology does the VXLAN header use a unicast address as its destination? Kind of an interesting way of wording this, but I really wanted to make sure that we understand what's happening underneath the hood of SDA when it comes to multicast. Remember that when we get a multicast packet in on a border node or an edge node, we need to decide how exactly we're going to get it to the destinations across the fabric. And Cisco gives us two different options for this, which incidentally is why we only have two answer choices here. First, we'll look at head-end replication, in which the head-end router, in other words, the router that's receiving the packet, is going to do the replication itself. That means in the case where we have two different destinations here that we need to reach out to, we are going to replicate that so that we have two packets, and each packet is going to get sent out the normal VXLAN tunnel to those edge devices. At this point, these are unicast communications, so our destination IP address will be unicast. So A is our answer. Now that said, if we have configured native multicast and our underlay is multicast capable, then we can send a single packet into the multicast domain and it will take care of the replication for us. At this point, when we send the packet into the underlay, this is a VXLAN packet whose destination is a multicast address. So again, when we're using a unicast address as the destination, that's head-end replication. If we were to use native multicast, that would be a multicast address as the destination. So again, in our case here, A is our answer. Last question. Which transit network type is able to natively carry VXLAN headers for policy enforcement? Well, once again, Cisco's only given us two different options, and so our answer choices are limited, and rather than make a bunch of stuff up, I just gave us an A or a B choice. So remember, when we have multiple fabric sites and we need to connect them to each other, we're going to have to connect over a transit network. And that transit network can be either IP-based or SDA. So per the question, we need to be able to use native VXLAN to tunnel among these different sites. And in order to do that, we are going to turn this transit network into an SDA transit. So B is our answer. Incidentally, if we can't turn our transit network into an SDA network, we would have to deliver an IP-based transit network. At that point, we wouldn't be using the VXLAN headers, unfortunately. We'd have to forward that packet de-encapsulated through the transit network and trust that the remote border router is going to handle the tagging that we need it to do for us. Well, that wraps up this quiz. If you find yourself missing any pieces of knowledge, then be sure to go back and watch the appropriate videos in order to obtain them. Otherwise, congratulations on completing design in SD Access Fabric. I hope this has been informative for you. I'd like to thank you for viewing.